Hi guys, welcome back. So today we're going to talk about 3.3 measures of relative standing, in box plots. So again, we're concluding the describing, exploring, and comparing data portion of our class in statistics. So when we talk about measures of relative standing, we're really talking about z-scores. So a z-score is simply a standardized value, and it's the number of standard deviations that a given value x is above or below the mean. Now the z-score is calculated by using one of the following. If we have a sample, we use the equation on the left, which is going to be our z equals x minus x bar divided by s, where x bar is our sample mean and s is our sample standard deviation. On the right, we have z equals x minus mu over lowercase sigma, where mu is the mean of the population and lowercase sigma is the standard deviation for the population. And when we're talking about z-scores, guys, and we're talking about a standardized score, it is so that we can measure different things on the same scale. So for instance, in the US, you have to have an ACT score or an SAT score to enter a four-year institution. Well, oftentimes the ACT scale and the SAT scale are not the same. And it's not oftentimes, it's all the time. They're not on the same scale. But there are some students who choose to take the ACT over taking the SAT and vice versa. So colleges have to have a way that they can standardize the value of the ACT and the SAT so that they are comparable. And this is why we have z-scores, so that we can standardize these values. So when we're dealing with z-scores, we're actually going to round off z-scores to 2 decimal places, such as they're going to have 2 values behind the decimal place or to the hundredths place. There are some important properties of z-scores, and the first important property is that a z-score is simply the number of standard deviations that a given value x is above or below the mean. Z-scores are expressed as numbers and they don't have units of measure. Now, a data value that is significantly low, it's designated that if its z-score is less than or equal to -2, which is 2 standard deviations below the mean, or the value is significantly high if its z-score is greater than or equal to +2, or it means that the value is 2 times the standard deviation above the mean. Now, if an individual data value is less than the mean, you're going to calculate the z-score and that value will be negative. So don't panic if you see a negative z-score because it is highly possible. So let's look at comparing a baby's weight and adult body temperature. So which of the following 2 data values is more extreme? And we want to know, is it more extreme relative to the data set from which it came? So we have 4,000 gram weight of a newborn baby among 400 weights with a sample mean of 3,152 grams and a sample standard deviation of 693.4 grams. The second example we have is 99 degrees Fahrenheit temperature of an adult. And among those 106 adults with a sample mean of 98.2 and a sample standard deviation of 0.62 degrees Fahrenheit. So we want to know which of these 2 would be considered to be extreme. Well, let's look at the solution. So the first thing we want to do is we want to use the z-score formula to calculate a z-score. So when we come back to the slide, you're going to see the actual worked out calculation. So let's go ahead, let's jump in and let's get started. All right, guys, so welcome back to our example where we're comparing a baby's weight and adult body temperature. If you notice, I've used the z-score formula that was provided to us in previous slides. And so we know that z is equal to x minus x bar divided by s, where x bar is the mean and s is the standard deviation. So basically what I've done is simply plug and play into the 4,000 gram birth weight, and we came out with a z-score of 1.22. Now for the body temperature, we're using the same formula, except for we're going to interchange those values for the temperature values that was provided. So we have a resulting z-score of 1.29. Well, because the body temperature has a higher z-score than the birth weight, we say that body temperature varies more than the birth weight. So the one with the more extreme values would be body temperature, and the one with the less extreme value would be birth weight. And the reason why is because the z-score for the body temperature is higher than the z-score for the birth weight. All right, guys, so I'm going to go ahead and clear this slide. And we're going to move to using z-scores to identify significant values. So if we're looking for significantly low values, their values are always going to have a z-score of -2 or less. If we have significantly high values, those are going to be values of a z-score that are 2 or greater. And any value that falls between -2 and 2 will be values that are not significant. All right, so let's look at this platelet count of 75, and we want to know if it's significantly low. The lowest platelet count in a data set is 75. Platelet counts are measured by 1,000 cells per U-liter. Is that value significantly low? Well, we assume that the platelet counts have a sample mean of 239.4 and a standard deviation of 64.2 cells per milliliter. So what we're going to do is I'm going to set this up, and we're going to look at the z-score value and to determine if it's significantly low to answer our question.